Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4. We're on chapter 15, Phosphorus, and today we'll be looking at climate change and the phosphorus cycle, and I think we will also be ending the chapter today. Climate change is an emerging topic in limnology as it is in many areas of environmental science. While numerous studies of climate impacts on aquatic systems have been conducted to date, the impacts on lake phosphorus cycles and what the future may hold remain unclear. A starting place to fill this knowledge gap is to identify factors that affect phosphorus exports and internal lake dynamics based on our current understanding of these processes and combine them with our knowledge of how climate change affects those factors. While speculative, informed speculation is the first step to designing research studies. Using this approach, we can identify climate-related factors such as precipitation patterns, storm intensity, frequency of droughts and floods, changes in soil moisture and runoff, atmospheric stilling of winds, lake flushing rates, and decreased ice cover for their potential to affect phosphorus exports from catchments and lake phosphorus dynamics. The majority of external phosphorus loading to many lakes enters via surface runoff. Hence, changes in discharge volume, storm intensity, and timing will affect export rates. Large storm events can flush dissolved and particulate soil phosphorus, resulting in large nutrient pulses to lakes, but prolonged storm will gradually dilute runoff concentrations. Large storms may also decrease lake residence time depending on the volume of runoff relative to lake volume. The frequency of large storms has increased in some regions in the continental USA, which suggests that long-term and short-term phosphorus export and timing of pulses may have changed. Storms or large snow melts that coincide with crop fertilization or buildup of soil phosphorus may export relatively more during runoff events. Drought deprived lakes new external loads of phosphorus while temporarily increasing residence times. However, base flow phosphorus concentrations are relatively high during prolonged periods between storms, and continuous base flow can export significant amounts of phosphorus downstream. Clarification of the impact of changing storms and runoff patterns on phosphorus exports will require long-term high-frequency monitoring of runoff and its phosphorus fractions in numerous catchments with varying land uses in different climatic regimes. Atmospheric stilling of winds over the past several decades in some regions likely reduced average turbulence in lakes, but changing frequency of high-speed windstorms will affect the frequency of episodes of wind-induced turbulence, which are important to resuspension and elimination of thermal gradients, especially in polymictic systems. Shorter periods of ice cover result in earlier onset and longer periods of thermal stratification, which means hypolimnetic waters may be deprived of fresh oxygen supplies for longer periods, increasing the risk of anoxia and internal phosphorus loading. Less ice cover also leads to prolonged exposure to wind-induced mixing events. Warmer temperature will increase microbial metabolic rates, but temperature increases will vary with seasons and regions. Productivity and therefore phosphorus cycling indirectly is also affected by cloud cover, which affects temperature and solar radiation. A note of caution is changes in climate-related factors, such as those described above, may not always be driven by climate change. In addition, they are not the only factors that can influence export and lake dynamics. Changes in land use, fertilization practices, agricultural and urban management practices, upgrades to wastewater treatment plants, and expanding human population will also affect exports, but their impacts may be difficult to distinguish from those caused by climate change when they occur. Coupled dynamic watershed lake models may be helpful in evaluating their relative importance. In summary, phosphorus plays a major role in biological metabolism in comparison to other macronutrients required by biota. Phosphorus is the least abundant and commonly is the first element to limit biological productivity. Many quantitative studies exist on the seasonal and spatial distribution of phosphorus in streams and lakes, as well as the loading rates to recipient waters from drainage basin. Orthophosphate, or PO4-3, is the most directly utilizable form of soluble inorganic phosphorus. Phosphate is extremely reactive and interacts with many cations to form, especially under oxidizing conditions, relatively insoluble compounds that precipitate out of the water. Availability of phosphate is also reduced by adsorption to inorganic colloids and particulate compounds. B. A large proportion of phosphorus in freshwaters is bound in organic phosphates and cellular constituents of organisms, both living and dead, and within or adsorbed to organic colloids. C. The range of total phosphorus in freshwaters is large, from less than 5 micrograms per liter in very unproductive waters to greater than 100 micrograms per liter in highly eutrophic waters. Most uncontaminated freshwaters contain between 5 and 50 micrograms of phosphorus per liter. D. Although concentration of total and soluble phosphorus of oligotrophic lakes exhibit little variation with increasing depth, eutrophic lakes with strongly clinograde oxygen profiles commonly show a marked increase in phosphorus content in the lower hypolimnion. Much of the hypolimnetic increases from soluble phosphorus near the sediment-water interface. 3. Dissolved phosphorus in rivers is generally higher than in lakes and often increases markedly following rainfall and snowmelt events on the drainage basin. A. At low concentrations in streams, phosphorus can be limiting, and microbial productivity often increases with increasing loading of phosphorus. B. In addition to biological uptake, phosphorus abundance is regulated by abiotic adsorption and desorption reaction with organic and inorganic particles. Dissolved organic phosphorus compounds are utilized more slowly than inorganic forms and tend to be exported downstream for considerable distances. C. Most of the recycling of phosphorus is associated with microbiota attached to particles. Less than 5% is associated with microinvertebrates and higher organisms. 4. Exchanges of phosphorus across the sediment-water interface are regulated by oxidation, reduction, or redox interaction dependent on oxygen supply, mineral solubility, and sorptive mechanism, the metabolic activities of bacteria and fungi, and turbulence from physical and biotic activities. A. In all but the upper few millimeters of sediment, exchange is slow and controlled by low diffusion rates. B. If water above the sediment is oxygenated, an oxidized macrozone is formed below the sediment-water interface, below which the sediment usually becomes extremely reducing. The oxidized macrozone effectively prevents phosphorus from migrating by diffusion upward into the water column. As the hypolimnion becomes anoxic in productive lakes, the oxidized macrozone is lost. The release of phosphates and ferrous iron into the water occurs readily when reducing conditions reach a redox potential less than 100 millivolts, uncorrected for pH. Soluble phosphorus can accumulate in large quantities in anaerobic hypolimnia. With the advent of autumnal circulation, ferrous iron is rapidly oxidized and precipitates much of the phosphate as ferric phosphate. E. Bacterial metabolism of organic matter is the primary mechanism by which organic phosphorus is converted to phosphate in the sediment and for creating the reducing condition required for the release of phosphate to the water. F. Movement of phosphorus from sediment interstitial water. F. Movement of phosphorus from sediment interstitial water can be accelerated by physical turbulence and by biota. If light reaches sediments, the photosynthetic activity of epipelic algae can create a highly oxidized macrozone in the superficial sediments and regulate phosphorus release to overlying water on a diurnal basis. I. Rooted aquatic macrophytes often obtain phosphorus from the sediments and can release some back into the water both during active growth and particularly upon senescence and death. Most of the released phosphorus is retained and recycled by attached biota. II. High population density of sediment-dwelling invertebrates such as midge larvae can increase the exchange of phosphorus across the sediments water interface. 5. Recent studies of phosphorus cycling in the trophogenic zone have demonstrated that the exchange of phosphorus between its various forms is often rapid and involves numerous complex pathways. A large portion, often greater than 95% of the phosphorus, is bound in the particulate phase of living biota, especially bacteria, algae, and other microbes. B. Organic phosphorus of the ceston of the open water consists of at least two major fractions, a rapidly cycled fraction that is exchanged with soluble forms, In this fraction, phosphate is transferred rapidly through the particulate phase, and II, a fraction of dissolved organic and a colloidal phosphorus material that is released and cycled more slowly. C. Phosphorus uptake and turnover kinetics in numerous lakes show that turnover rates are extremely rapid during summer periods of high demand and low loading inputs. D. Flagellates over protista and zooplankton that feed on bacteria and other cestone excrete soluble phosphorus and ammonia. These nutrients are rapidly utilized by algae and bacteria. E. Phytoplankton requirements for phosphorus are variable among species and can lead to selective advantages of certain algae as phosphorus supplies change seasonally or as phosphorus loading to freshwater change over a longer period of time. 6. Sedimentation of particles results in constant losses of phosphorus from the trophogenic zone. As a result, new phosphorus supplies must enter the ecosystem in order to maintain or increase productivity. A. Phosphorus enters freshwaters from atmospheric precipitation and from groundwater and surface runoff. The loading rates of phosphorus vary greatly with patterns of land use, geology, and morphology of the drainage basin, soil productivity, human activities, pollution, and other factors. B. When phosphorus is added to unproductive freshwaters, either experimentally or as a result of human activities, the usual response is a rapid increase in phytoplankton productivity. Inputs must be more or less continuous, however, to maintain a higher level of productivity. C. Numerous steady-state and dynamic mass balance models have been developed to predict, on the basis of phosphorus loading and retention times, the anticipated response of algal biomass and productivity. The model predicts a reasonably accurate estimation of permissible phosphorus loading needed to achieve a certain level of productivity if loading is lowered. D. In certain shallow lakes with greater than average turbulence, large littoral areas and small anaerobic apolimnia, reduced productivity does not always occur as rapidly as reduction in external loading, as predicted from some models. 7. The impacts of climate change on phosphorus dynamics are not well understood yet, but climate change related changes in precipitation pattern, storm intensity, frequency of droughts and floods, changes in soil moisture and runoff, atmospheric stilling of winds, lake flushing rates, and decreased ice cover have potential to affect phosphorus export rates from catchments and lake phosphorus dynamics. And that will be it for this chapter. Thank you for staying on and being patient with me and discovering the wonders and the mysteries and the science behind phosphorus cycling in lakes and rivers. And we'll see you next time for chapter 16. Other important elements, yeah. So I guess iron and manganese and the sulfur cycle and silicon and other minor elements. So that's what the next chapter will be, and I will see you then. Bye.